Thank you so much for being here. The weather is nice and you're interested in science, so it's so good that you're here. I will talk about this specific type of stars that we can use to better understand our sun, and among other cool things that I will talk. So basically, I will talk about how hard it is to estimate the stellar ages and what are solar twins, some ways that we can understand stellar evolution, especially of stars that look like the sun, and finally, if I have time, the solar twins and the search of exoplanets and maybe life. So to start with the challenge of stellar dating, I will first start with why do we try so hard to estimate ages? It's basically because the stars, they evolve over billions of years, and we know as humans that over that time, can you imagine how many things could happen? And if we know the age of a star, then we can, for example, guess the age of the planet, and we can track the evolution. So if you're interested in evolution, in astrophysics, then in astronomy, then it's important to have like precise ages. And nowadays, our uncertainty in ages, they are so big that for stars, for example, the sun, it's like 4.6 billion years old. And it's like not knowing if the sun has just born or is about to die. It's a huge error in age. And the star, it co-evolves in the environment that it is in. And it doesn't matter if you're interested in the stellar formation, planetary evolution, galaxy evolution, of how the galaxies are formed, ages are important, and they are essential. So to start, the definition of age for humans is quite simple, because we can see like a baby is born, and we can see and we count this day zero, and we use the calendar to estimate, not to know the age, and it works the same for everyone. Sometimes we have different records or the wrong age, but the person knows its own age. And for stars, this is not as simple, because for stars, the day zero, we say that the day zero is when it starts burning hydrogen in its center. And so this is what we call the beginning and the main sequence phase. And the star spends most of its life during the main sequence, and it changes very little. So the star basically looks the same during this phase. And the problem starts even when the star is born, because it is born inside this huge clouds of gas and dust. So the star is hidden, and we don't see it. Like when a baby is born, you see it. And when a star is born, you don't. It's hard to see. And the other thing is the time scale, because for humans, we work with years. And for stars, we try to use the same way. Like the definition of years for humans, we use the same for stars. But the evolution time scale for stars is in the billions of years. So this is another way it's difficult, because we try to apply like human ways of measuring things to things that evolve differently. And how do astrophysicists track these evolutionary stages? We basically use the Hertzsprung-Russell diagram. Probably some of you already know about it, but if you never heard about it, I will start with a hypothetical human diagram, so you have an idea how this works. So for humans, we could have some properties, like human properties, we could measure. And for example, we could collect data from people for their height. And I don't know how exactly we could do this, but count the line expressions, like how old a person would look like. And we collect this data, and then we can populate this diagram. And imagine that we have this model that tells, like, if you have the height and the line expressions, then you can guess the age of the person. If you compare, for example, a baby with an elderly person, then it's easy to guess which one is older. But in the adult phase, it's very difficult to do this, because basically when you're an adult, you change very little over many years. So for example, for example, I know my age, and I could try to guess your age, because I know my age. And I don't know if you can see the issue behind this, because we are different. We have different genetics, different origin, different diet, different everything. So I could use this information, but I will not be precise. So I cannot guess your age precisely. So this is how it looks like for astrophysics, for stars. So the properties, the stellar properties, basically the luminosity and the surface temperature. And when we populate this diagram with the stars, with what we know from the stars, it gathers in different groups. And the sun, for example, is in this region, which is the main sequence. So the sun is here. And the solar twins, which I will explain in a bit what they are mainly in this main sequence. And they change very little. So the main sequence phase is almost like our adult phase. So we change very little. So in the star change very little. So how can we do this? So this illustrates the changes of the stars. So the star is born in this huge clouds of gas and dust, and it spends most of its life during the main sequence changing very little, and then it starts to expand. And when we look to a red giant, for example, we can know that this star is older than the sun. But when we look to a star that it is in the main sequence, it's difficult to tell if the star is older or younger than the sun. And how can we do this? So basically, we use solar twins. And this kind of stars, it's basically like me. Instead of I will try to guess your age from my age, I will try to guess my age from comparing to my cousins, because they are very similar to me. So then I can have like a more precise values. So it's a fair way of comparing, comparing similars. So what are these solar twins? Basically, despite of the name might give this impression that they have the same age, but it's not. Basically, they just look like this. They look the same. Some people might say that should be like solar doppelgangers instead of solar twins, but we call it solar twins because someone gave this name like a long time ago, and so it's solar twins. And they are old or young, or they could be at the same age as the sun, but they are similar to the sun in properties as the surface temperature, the mass and the radius, and in one of the important ones is the most important one is the chemical composition. So basically is how abundant some elements are in a stellar atmosphere. And for the sun, for example, we can measure the stellar, the sun composition, chemical composition in laboratories. So we have like these meteorites, and we measure how much of each element we have in the meteorites. And we say that this reflects the amount of elements in the sun because they were all born together from the same cloud, in the same cloud, so they are supposed to have the same chemical composition. And another way of doing this is to see the sun, use the sunlight. So we separate the white light in different colors, and in this light we can see some signs of elements, different elements. And from other stars, we don't have this meteorite. So what we can do is compare the sunlight with the starlight, or you can use the starlight to get the chemical composition of the star. And in the case of solar twins, we are comparing similars, so it's easier to see small changes because they are very similar. So we can more precisely see these changes. In the solar spectrum, for example, we see this separation of light as in rainbows, but this is one form, which is the refraction. But the other thing that we mostly use now is the diffraction, because it separates the light in a way that it's easier to turn this into numbers and this into tables, and then we do like the statistical things behind it, and we measure the light. So in the right is the solar spectrum, and in the different colors, and these dark lines is the absorption lines, and they are basically because the atmosphere has its elements, different elements. These atoms interact with the light, and parts of the light is absorbed, and it leave a print of this element in the spectrum. So basically, it's a map of the elements in the stellar atmosphere. In this case, in the sun's atmosphere. So with this, we can measure the abundance of different chemical compositions. And for the other stars, we can do the same. So basically, we have these billions of stars in our galaxy, and we can point telescopes to these stars. We collect their lights, and we separate in different colors. We see these different absorption lines, and we estimate the chemical composition, and we can compare to the sun. Some of these stars, they are solar twins, and then we get like many spectra from different stars, and we compare it. But one thing is that we cannot compare, for example, the sun with the other stars. If the sun, we have this much details that we don't see from other stars, because the stars, they are far from us. So what we do is, in this picture, for example, it's like day, and during the day, everything is reflecting the sunlight. And here we have this beautiful object, which is the sun, the moon, and the moon is reflecting the sunlight. So what someone thought like many years ago is, what if we took this reflected sunlight? It will look like we are observing the sun as a star distant from us. So instead of looking the sun directly, we look at the reflected sunlight. So this will make the sun look like a distant star. So now we are observing the sun as a distant star. And this is basically what I do in my work. So I compare the stellar spectrum with the sunlight, the solar spectrum, from this reflected object. So in this case is the moon, but we could do this for asteroids or dwarf planets. So any object in the solar system that reflects the sunlight. And then we have this. We can fairly compare more fairly. Okay, so we could have an idea. So you can have an idea how similar this kind of stars are to the sun. I have here a plot. So basically here is a spectrum, a solar spectrum and a solar twin spectrum. And the x-axis is like the colors that we are seeing. So instead of the colors, it's the number, so it's the wavelength. And these dips is because the flux that we are measuring, it's lower because this specific element is absorbing the light. So we are comparing, so we are seeing this prints of elements, different elements. The red circles are from solar twin, and the solid black line is from the sun. So we basically cannot distinguish between those two. Or can you distinguish between those two? So they basically look the same. And because they are so similar, we can detect these small changes which happens during the main sequence. So we can guess if the star is older or younger than the sun. And this extends to the whole spectrum. So from that, so we use this method, and then we can get like the highest precision in age possible for stars. And because of that, using solar twins, this could help us better understanding stellar evolution, and those precise ages could also be applied to other type of other scientific subjects. So, and now I will talk about the evolution of the sun and the solar-like stars, which is basically what I do now. So in my work, what I'm doing is looking for other properties, not only the temperature and the mass and radius and chemical composition, but also other things that might change during the main sequence phase. So we can tell if the star is older or younger than another star. In our case, we compare to the sun. One way of doing this is seeing the stellar rotation. So at the beginning of the life, the star rotates really, really fast. And as the time passes, the star this slow down. So we can see that if we get the rotation of the star, we can estimate the stellar ages. And this plot shows the brightness of the star. So it's basically how bright a star is. And in the x-axis is the days passing. So this periodicity is basically because of the rotation of the star. So if the star rotates fast, then we have this short periods. And if the star rotates slow, then we have these long periods. And this is basically because the star has some spots in its surface, and because it's rotating, we see these changes in the brightness of the star. Another way, another property that we could measure is how strong a magnetic field is. So at the beginning of the life, the magnetic activity of the star is really strong. And then as the time passes, it gets weak. So we can notice these changes to estimate the age. So I don't know if you noticed, but the x-axis here, so if I put like an arrow here, will basically be the age. And this also applies to the magnetic activity. So this is basically the age. And this is what I do. So when I have a recent work where I'm suggesting a new relation that you measure the activity level of the star, and you can guess the age. But we expect that stars, because of the stellar diversity, the stars, they are different. They should evolve differently. And this relation should account for the chemical composition of the star. So what I'm suggesting is this relation dependent on the chemical composition. So here in the y-axis is the magnetic activity, so how active a star is. And if it's higher, it's a strong activity. And if it's lower, then it's a weaker activity. But it depends on the chemical composition, which is represented in the colors. And the x-axis, again, is the age. So basically, what I'm saying is that the stars are different, and they evolve differently. And it's good that we can compare similars to similars to guess precisely their age. And finally, the solar twins and exoplanets, which is something that I'm starting to work on right now, especially because I'm here. So this work I've been talking about until now is basically what I do in Brazil, my research group in Brazil. And I came here because there are many experts in exoplanets, and they have, I will tell you about the project that Exeter is being part of. So we could use these solar twins at these precise ages to better understand exoplanets. So since the beginning of before 1995, when the first exoplanet was discovered, we asked ourselves, not me because I wasn't alive, but we asked ourselves that why, if there was planets orbiting other stars. So can you imagine that not so long ago, we didn't know that exoplanets were there. We suspected, but we didn't know. So then we had this first detection of exoplanets, and they noticed that if we use, for example, different instruments or different methods, it's hard to detect these exoplanets because they are very different. The data is different. So there was this need of a new instrument that with high quality data that could observe the stars in the same way during a long amount of time. So they start this new generation of instruments of high precision that could give you a high precision data. So HARPS is one of those, and it's the original one, because after that they start building new instruments like HARPS. So we have the HARPS 2, and now there's going to be a HARPS 3. And this is basically because of the success of this instrument and how useful it is. And the data I use in my PhD, it's basically all from this instrument. So in the right is the building. This is, and you can see the dome, and is an observatory in Chile. So inside this building, you have this telescope in the left, and this telescope has a 3.6 meter mirror. So the mirror collects the light, and the light goes through a fiber, and so basically it's collecting the white light of the stars, and then separate in different colors. And we measure the chemical abundances, or whatever. There's many things we could do. So there are many different types of exoplanets, but the easiest ones to detect are the biggest, because our way of detecting all different methods to detect exoplanets is based on how much a planet can affect the star. Or, for example, the stellar brightness, because the planet is passing in front of the star, or the velocity of the star because of the gravity. So if the planet is bigger or the star is smaller, then the impact of the planet on the star is easy to detect. But for smaller planets, it's hard. It's even harder. So now there is this effort of scientists together. So in the UK, for example, the whole UK working with people in the US, and they are creating this new project to search for planets like the Earth, so Earth-sized planets. And so Exeter is part of this Terra hunting experiment, which is this HARPS 3. So it's like the first instrument that I told you about. And this is going to be installed inside this telescope. So this is the building. There is this telescope inside it in La Palma. And it will observe for 10 years a specific type of stars. And now what I'm doing here is basically trying to convince them why it's important to look for solar twins. So because they are in that phase of target selection. So maybe they will observe solar twins. And if they do, there are many things that we can, many science that we can make it. So now, from now on, I will talk about my future goal specifically, and I hope that this makes sense to you, and we can discuss about it. So basically, I went to the Natural History Museum 2 weeks ago, and then I saw these different fossils, and there is, I don't know if you have been there, but there is this part where they tell about the human history, and it's just like a short amount of time comparing to the Earth, to Earth's history. So the complex forms of life, they only appear like 600 million years ago. For humans, it's like a lot, but for Earth's history, is a really short amount of time. And the precision in ages for solar twins that we can get is basically in this time scale, in millions of years. And the typical precision in age is in billions of years. So they cannot discern if, like in time scales of life evolution. And the other thing is that there are many hypotheses of the origin of life, and one of them is that the changes in the Earth's atmosphere could make this perfect place for life to develop, to evolve. And so the changes in, like, the Earth was hot, and then there was like an ice ball, and then it's like more or less how it is today. And this is basically, again, if you look like in the x-axis, let's pretend it's an x-axis, it's basically age. So if we don't know age, we cannot build this kind of things. So imagine if we know age, and if we could detect the atmospheres of these planets, which is something that's happening now. So people are looking through the atmosphere of exoplanets. And if we detect life, we could do these kind of things. So building, like, look at the babe Earth, and then look at the old Earth, and understand more about ourselves. So using these precise ages could help us understanding these planetary and life evolution and how I am with time. Okay. So, but yeah, I'll be finishing. And so basically, solar twins can be used to better understand the solar evolution and sun-like evolution. We get the highest precision in age possible. So they are really useful if you're interested in evolution in general. And the ultimate goal, at least for me, and I think many people here in Exeter, in the department I'm working on, is identifying exoplanets that could be inhabited, or will be, or was, but you can understand this. And yeah, that's it. Thank you.